So in today's video, we're going to combine what we have just learned about hypothesis testing with what we learned in chapter 10 about confidence intervals. The two are actually related when you look at a two-sided hypothesis test or a two-tailed hypothesis test, okay? So if we look back at chapter 10 and we looked at a confidence interval that we were hoping would contain that population mean, if we knew what the population standard deviation was, so if we knew what the population standard deviation was, then you could create this confidence interval. And it was given by the sample mean plus or minus this z value multiplied by the standard deviation over the square root of the sample size. And we would hope that this confidence interval would contain our population mean with a certain level of certainty, okay? Because we would be a certain level of confident, let's say like 95% confident, that this interval would contain the population mean. Okay. And this would be at the 100 times 1 minus alpha percent confidence level. Okay. Again, your calculator will compute all of this for you, so don't worry too much about it. But if we knew what that population standard deviation was, and we wanted to be a certain level of confident that our population mean would be contained in this interval, we would go ahead and create a z interval. Because we know what our population standard deviation is, we're going to use a z interval, okay? So the confidence level and the amount of confidence that you want to have that this interval will contain that population mean depends on how big this interval is going to be. The more confident you want to be that this interval contains that population mean, the larger that this interval has to be. Okay. So we went through that, and then we also went through a t interval, okay? You're going to use a t interval when you only know the sample standard deviation. You don't know the population standard deviation, you only know that sample one. What we're going to do in this chapter is we're going to relate this to what we have just learned about hypothesis testing. And it's actually, confidence intervals are another way to perform a hypothesis test. So let's say that you have, it has to be a two-sided hypothesis test. So for a two-sided hypothesis test, okay, let's say that you had your null hypothesis was that the mean was equal to some value. We'll call it mu0, okay? So that the mean is equal to some value, but then you had some other sample data that suggested something else. So we could say that the mean actually wasn't equal to that value, okay? This gives us a two-sided hypothesis test because you have to look at whether the mean is in fact greater than that value or less than that value. All we care about is that it's different. We don't care about whether it's one or the other. So let's say that you want to perform a confidence interval on this. So let's say you want to be 95% confident that that interval will contain the population mean, okay? So for a 95% confidence interval, you are 95% sure that that interval will contain the mean, okay? So if you are 95% confident that that interval contains the mean, okay? So this interval is the sample mean plus or minus something. So let's say we know that our sample means are normally distributed, okay? Sample mean of whatever your sample is in the middle, and you've got plus or minus that value, okay? If you are 95% sure that this interval contains the population mean, then you should be able to find two values here and here such that 95% of the data lies in the middle, okay? That means if your population mean is close enough to that sample mean 95% of the time, that means that 5% of the time it's going to be too far away from that sample mean and it's going to fall outside of that interval, okay? So that means that from a 95% confidence interval, 95% of the time, our population mean we think will fall within that range. Okay, it will fall within that interval. But 5% of the time, so put 0.025 on either side, 5% of the time, our population mean is going to fall outside of that interval. That means that 5% of the time, our population mean is too far away from our sample mean. So because our sample mean and our population mean differ too much, and they suggest different things, we would have to reject that null hypothesis because we can no longer consider the population mean to equal what we initially thought it was. And we have to go for the alternative hypothesis because our sample mean and our population mean are just too far apart. And that means that our sample mean is actually suggesting that the mean is something else. So let's put this all together again. If you create, in this case, a 95% confidence interval, okay, you create a 95% confidence interval, and that confidence interval surrounds the sample mean. So it's the sample mean plus a value, sample mean minus a value, okay? So you've got this confidence interval that surrounds that sample mean. What we want is that 95% of the time, this is when we did confidence intervals in chapter 10, 95% of the time, we want that population mean to be within that interval. Okay, so it falls within the interval 95% of the time. That means that 5% of the time, it is too far away from the sample mean. So 5% of the time, it is outside of the interval and there is too much of a difference between what our sample data showed the mean was, so between the sample mean that we got and the population mean, okay? So if we come back here, 5% of the time, you could have a population mean that fell out here, okay? So we would expect 5% of the time, the interval that we calculated for whatever sample we took that time, 5% of those intervals would not actually contain that population mean, okay? 95% of the intervals that we create are going to catch that population mean. But we may come up with a sample where the sample mean and the population mean just differ too much. So 5% of the time, we're going to expect that population mean to fall outside of that interval. That means that at that point, I have too much of a difference between my population mean and my sample mean. My sample mean is just too different from my population mean. Therefore, I cannot consider my population mean to be what I thought it was if my population mean falls out here. Okay, so if you go ahead and calculate a confidence interval and that population mean that you thought you had falls outside of that range, it means that your sample mean and your population mean are just too far apart. And your sample mean is saying something that is way different from what your population mean is. Therefore, we can no longer consider this value to be our population mean, which means that we would have to reject our null hypothesis in favor of the alternative. Okay, so the moral of the story is, if you go ahead and conduct a confidence interval for whatever level of confidence they give you, let's say 95% confidence interval, okay? You go ahead and you create that confidence interval, given the sample statistics that they'll give you. They'll give you like a sample mean, and then they could give you a sample standard deviation or a population standard deviation. Population standard deviation means you go ahead and do a z interval. So if given the population standard deviation, you go ahead and create a z-interval. Okay, exactly the same as we did in chapter 10. If you are given instead just a sample standard deviation S, you go ahead and use a t-interval. Okay, now you go ahead and you find that interval with whatever sample data that they have given you. Then you can go ahead and create these two hypotheses depending on what the question is asking. So they could say, okay, we think our mean is this, but because of our sample data, we think that it might actually be different to this. Let's test out this theory. So you will create your null hypothesis and your alternative hypothesis. If in fact this value that you have here, we call mu0, the value that they thought the population mean was, if that value falls within that confidence interval, whether it be a z-interval or a t-interval, if that value falls within that range, your sample mean and your population mean are close enough together, and that means that your sample mean is close enough to your population mean that we don't have to consider the population mean to be any other value, and we can go ahead and fail to reject our null hypothesis and accept it for what it is. However, if you find that your population mean value falls outside of the interval, we have to go ahead and reject our null hypothesis because our sample mean and our population mean are too far apart. They are suggesting completely different things, which means that we would have to reject our null hypothesis in favor of the alternative because the sample data actually said, well, the mean is just too far away. We cannot consider the population mean to be what it originally was, given what our samples showed us. Okay, so that's the moral of the story. If our population mean falls in the interval, then you're going to fail to reject. Okay, population mean and the sample mean are suggesting the same thing. So your sample data is suggesting the same thing that you originally thought with your population data. So you're going to fail to reject. Okay. But if it falls outside of the interval, so if the population mean falls outside of the interval, that means that you reject the null hypothesis in favor of the alternative hypothesis. Okay, so you actually therefore say that the population mean has changed. It's not equal to that value mu0 that you initially thought it was. Okay, let's go ahead and do a quick example. So in this example, and this is in the notes, so if you actually want to go ahead and read this, it's right at the end of my notes. For 11.3, it says an engineer has calculated the maximum horsepower for an engine to be 620 horsepower. 9 engines are randomly selected for horsepower testing. The sample has an average maximum horsepower of 690 with standard deviation of 60. Assume the population is normally distributed. Calculate a confidence interval for the average maximum horsepower for the experimental engine. Use a significance level of alpha is equal to 0.05. So, a couple of things to note here. Number one, it says in this problem to assume that the population is normally distributed. Remember when we did confidence intervals, okay? When you take a sample, in order for these sample means to be normally distributed, you either needed to have that the population was normally distributed to start with, or that your sample size was greater than 30. Here we have a sample size of 9. So in order to know that we can use that normal distribution of the sample means, we have to know that that population is normally distributed, okay? Because our sample size is too small, okay? So we know at the moment our sample size is 9, our sample mean was 690, and the sample standard deviation was 60, okay? Now, they think that the population mean is 620, so our null hypothesis would be that the mean is equal to 620. That's what they think that population mean is. But what they want you to do is to go ahead and calculate the confidence interval and test this where they actually think that the mean is different to 620. Okay? We don't know whether it's going to be greater than or less than. Okay, whenever you deal with confidence intervals in this situation, you're dealing with a two-tailed hypothesis. So whenever they give you one of these hypothesis tests to do and they say to use a confidence interval to do it, your alternative hypothesis is always going to be two-sided. Okay, so this is what we have so far. And the other thing that they have given you is the significance level of 0.05. That means that we want to reject the null hypothesis 5% of the time. Okay? Which means if we want to reject the null hypothesis 5% of the time, that means 95% of the time we want to fail to reject the null hypothesis. We want to be in favour of that null hypothesis. Which means if we want to be in favour of the null hypothesis 95% of the time, 95% of the time we must have that our mean will fall within this confidence interval that we're about to calculate. Which means that we have a confidence level of 95%. Okay? Because the significance level shows us the percentage of time that we want to reject our null hypothesis, which means that we will want to fail to reject it 95% of the time, which means 95% of the time my mean and my sample mean, my population mean and my sample mean must be close enough together that we want to fail to reject the null hypothesis, which means 95% of the time our confidence interval will contain that population mean, which means I am looking at a confidence level of 95%. That's how these two things relate. So in this case, we now have our confidence level and we have some sample data, and we want to go ahead and test this hypothesis using a confidence level. So we have been given a sample standard deviation. So we have S. So we know that we have to use a T interval. If we have been given sigma, the population standard deviation, we'd use the Z interval. So we have S, which implies we use the T interval. So if you go ahead on your calculator and go to where the T interval was, so it was stat, go across to tests, and then scroll down on my calculator, it's option 8, okay? So stat, tests, and then T interval, okay? Here we're putting in statistics. So the sample mean X bar was 690. The sample standard deviation was 60, SX is 60. N is the sample size is 9 and the confidence level is 0.95. Remember to put it in as a decimal. And you go ahead and calculate. So I then get my confidence interval, my 95% confidence interval would be 643.88 to 736.12. So at the moment, forgetting the hypothesis test part of it, I am 95% confident that this interval will contain my population mean. The question is, does it contain my population mean? Well, my population mean is 620. 620 falls outside of this range, which means that there is too much of a difference between my sample mean and my population mean, which therefore means because mu is equal to 620 falls outside of this range, we reject the null hypothesis. So we reject H0, okay? And we reject it in favor of the alternative. So this tells us that our population mean is in fact different to 620, okay? Because our population mean and our sample mean were just too different from one another. There was too much of a difference between 690 and 620 in order for us to really consider 620 horsepower to be the mean, okay? So you can go ahead and put it back in terms of the problem and say that there is sufficient evidence at the 0.05 level to say that the maximum horsepower is actually different to 620. Okay, we have sufficient evidence to say that it isn't 620 horsepower. It's actually different from that. Now, although we have a value here that's greater than 620, we cannot say it's greater than, okay, because what we have tested using a confidence interval is that it is just different from that value. Okay, so always remember what you are actually proving. Okay, because we are using confidence intervals, it has to be a two-sided alternative hypothesis. So all we've shown here is that it's different from 620. Okay, so all you do here is just go ahead and create a Z interval or a T interval, and then you look at whether your population mean is actually within that interval or outside it. If it's outside it, then you're going to say that you're going to reject that null hypothesis in favor for that two-sided alternative hypothesis. That's the end of this video. If you have any questions, please feel free to ask me, and I will be more than happy to help, and I will see you in the next video.